In this system complexity, analog IC designs deal with several hierarchy and abstraction levels. This distance 500 micrometer, electrochemical sensor, AU microelectrodes, this one, potentiostatic, delta, summation M, digital input output, digital filtering, this is digital filtering, this is full potentiostatic, delta, summation M. This is electrochemical smart sensor, this is full. Okay. Here feedback DAC digital to analog converter, current sense, electrochemical sensor, VRW, V reference voltage, VRW, potentiostatic, delta summation M, sum and hold, digital filtering, D sense, Q mode. This is system complexity. Analog IC designers deals with the several hierarchy abstraction levels. Here hierarchy of the abstraction levels. In x-axis, functional, Verilog, VHL, system CEMS, SPICE, Simulink, electrical, SPICE, physical, FE simulators. Y-axis, system, circuits, devices, bottom up, top down. Here this side for full functional, here electrical, here physical. This is devices, here circuits, whole system. Devices, circuits, their codings, and function, here systems. Here Verilog using VHL systems, CMS, SPICE, Simulink, electrical, SPICE. System complexity, say mixing different abstraction levels during design. Mixing different abstraction levels during design. Feedback DAC, I sense, here inside the circuit, here in V reference, this coding, here in D sense, this much, here digital filtering. Simulation speed up, study of circuit non-ideal effects, multi-level and multi-domain simulation needed single engine clue approach, ASIC development, typical project scheduling, custom library, test chips. Here specification, design, integration, testing, this color. Specification MO up to 24. Specification, design, integration, testing, complete system chip. Here month, first 2 month specifications, 7th month to 6th month design, 6th month to 12th month integration, 12th month to 18th month testing, 18th month to 24th month complete system chip. Alignment with the foundry, fixed and calendar, long design iterations type 6M, first complete prototype greater than 18M. Complete system chip. CMOS technology cost full mask regular run depending on process modules. One layer divided by mask 36 mask set 25 millimeter layer 1 here up to layer going 25 millimeter stripper reticle wafer map full wafer map example 0.15 micrometer 16 of IP6M CMOS technology 1P6M dia size less than 625 millimeter square mask cost 100 pounds processing cost 2k pounds per wafer samples greater than 50 dia wafer intended for full production greater than 200 wafer per year. CMOS technology, that is CMOS technology cost full mask regular run multi-project wafer run for multi-wafer project for wafer. There one layer per mask 36 mask set. Okay. Design 1 design n number 25 mm to step curly wafer map dia 200 mm. Example 0.15 micrometer 1P6M CMOS technology dia size greater than 4 mm square mask and processing cost 1k pounds per meter mm square samples less than 100 intended for prototyping. Here CMOS technology cost same full mask regular and multi-project wafer and multi-layer multi-project wafer here multi-layer mask engineering run 4 mm M for multi, L for layer, M for mask. Here M for multi, E for project, W for wafer. 4 layer mask, 9 mask set. Layer 1, layer 2, layer 3, layer number 4. 12.5 meter, 12.5 mm here up to here. 12.5. So stepper vertical wafer map dia 200 mm. Okay, 0.15 double micron IP6M CMOS technology 1P6M CMOS technology die size less than 156 mm square mask cost 25 kilo pounds processing cost 2 kilo pounds per wafer 6 wafer lots samples greater than 200 die per wafer intended for small series less than 100 wafer per year. Full mask run same CMOS technology cost full mask run multi-project wafer MW run multi-layer mask MLM engineer here 9 mm. Here what we have seen 4 mm. Here 9 1 2 3 4 5 6 7 8 9 9 layer per mask 4 mask set 8.3 mm 8.3 mm up to here. Okay. Stepper reticle wafer map 200 mm. Okay. Here same 0.15 micrometer 1P6M CMOS technology die size less than 65 mm 69 mm square mass cost 12 kilo pounds processing cost 2 kilo pounds per wafer 6 wafer lots samples greater than 450 die per wafer intended for small series less than 100 wafer per year. CMOS technology cost full mask run, multi-project wafer, MW run, multi-layer mask MLM engineer run. Here wafer scaling switching run. One here 36 mask per set, one layer per mask, 36 mask per set. Block 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 25 mm, 25 mm step by rectangle, vertical single chip. This is single chip, wafer map, single chip, 0.15 micrometer, 1P6M CMOS technology, die size 150 into 150 mm square, mask cost 100 K pounds, processing cost 2K pounds per wafer, samples one wafer intended for limited series, low yield acceptance for images. CMOS technology finish, from the idea to the chip finish, device modeling for unlock design. Bulk enhancement MOSFET. Bulk enhancement MOSFET. Intrinsic and extrinsic model parts. Here, this is cell. Okay, this cell. Length is width. Okay. Here, base, source, gate, drain. Okay. Capacitor in between source and drain. Gate, diode in between D to resistance B, P1 to this bulk enhancement MOSFET. That's the extensive model parts. In this, bulk enhancement MOSFET, intensive extensive model, analytic physical versus numerical fitting modeling. Here, fitting and here type model BSIM 323 WN version 3. Here, save data available here. Data sheet, like data sheet, this one, factory data sheet. Okay. Here, in intrinsic extrinsic model parts, up to here process, up to here threshold voltage, up to here the mobility. This part mobility, output resistance, sub-threshold, charge model, substrate, junction diode, overlap cap, thermal model, noise model, this side too. Okay, like this, scaling. Accurate results from electrical simulation, too complex for handle design. Okay, size is it person model minus PSIM 33 type N version 3.2 for param equal to 1 param HK. Bulk enhancement MOSFET. If you enlarge this option, we can discuss no problem. But we need more knowledge, then only we can understand. We have to concentrate we have to comparison, especially then we will see afterwards. Bulk and this is a circuit schematic diagram, block diagram. So inside the circuit, how is that? Bulk enhancement MOSFET, classic large signal I/O